Thank you, everybody. Welcome back to the second colloquium of the year. It's my pleasure to introduce today's speaker, Chandrashekhar Khare from UCLA. Chandrashekhar got his PhD from under the supervision of Aruzoida and Dinakar Ramakrishnan, and is mainly known for his work on Galois representation, in particular the proof of Serre's conjecture. He is now a professor at UCLA. He has won several prizes for his work, such as the INSA Young Scientist Award, the Fermat Prize, the Infosys Prize, and the Cole Prize. He has been an invited speaker at the ICM, the International Congress of Mathematics, and he is a fellow of the American Mathematical Society and of the Royal Society. And today he's going to talk about modularity of Galois representation from Ramanujan to Serre's conjecture and beyond.
Thank you, Giovanni, and thank you again to the Montreal Number Theory group for hosting me, Patrick for the invitation, and the nice week I've spent here. So now this is going to be another kind of historically oriented talk. Where yesterday I talked about the proof of modularity of elliptic curves and kind of developments of it, starting with the work of Wiles in 1994. Now this work I'm going to talk about, of course, I'm going to start much earlier, but I'm going to talk about something about Serre's conjecture, which with my French colleague Jean-Pierre Berger, we proved around 2005 when I was last year in Montreal. So at that time, Jean-Pierre and I were both here, and there was some conference, and some of the work on Serre's conjecture kind of did happen. Some of our discussions happened in the city. So it's good to be back and talking about this. Okay, so let me see if what do I do to clip this forward? So I'm going to start, though I'm going to come to this Serre's conjecture. I'm going to try and draw a line between a paper of Ramanujan in 1916 entitled On Some Arithmetical Functions, and the kind of the influence it had on number theory throughout the course of the 20th century. So this paper of Ramanujan had some sort of interesting observations and conjectures, and somehow that they influenced the development of number theory. And I feel there's a direct there's a natural link between what Ramanujan did in this 1916 paper and what led to Serre and developing and Swinnerton-Dyer developing the theory of mod P modular forms and congruences between them, which in some sense led to his modularity conjecture, which is related to Wiles' work on Fermat's last theorem. So there's kind of some sort of story to tell, which is what I want to tell you. So most of my talk is going to be historical, but I'll kind of in the end mention a couple of open questions related to Serre's conjecture. I mean, mod P Galois representations and mod P modular forms. So Serre's conjecture, in some sense, is the mod P version of this class of the Langlands program. Okay? So the Langlands program is kind of this famous program which emerged in the 1960s, and Serre's conjecture, which perhaps emerged in the 1970s, is a kind of some mod P analog of that. Right? It's maybe though the Serre's conjecture itself is known, it is just this first case of a series of conjectures what people have made, and I think in some sense there's a lot to be done still here. So that's what I'm going to talk about, starting with 1916 and trying to get up to now, passing through the time when the work of Wiles and our proof of Serre's conjecture. Okay, and as I said, besides the history, I'm also going to then talk about a little bit about some couple of questions related to the Serre's conjecture, which are still not known, and especially a question about counting mod P Galois representations of a certain sort. Right? So even the finiteness of the count you're making results from Serre's conjecture, but exactly how many there are is still an open question. So that's roughly the plan of the talk. Okay, so this paper of Ramanujan is about something which is now called the Ramanujan tau functions. So these are Fourier coefficients of a particular modular form, a cusp form of weight 12 and level 1. Right, so this is a complex analytic function, and perhaps Ramanujan was the first person to look at the Fourier coefficients of these and kind of make observations about the arithmetic nature of these Fourier coefficients, right? Which are the Fourier coefficients of a complex analytic function, but somehow they have great number theoretic significance. So I want to start like from Ramanujan 1916 paper and look at the conjectures he made about the tau function, and somehow the first case of Serre's conjecture we proved, Jean-Pierre Berger and I proved in around 2004 was to do with the Ramanujan's tau function and these particular the Galois representations which are supposed to come from such an object. So somehow it's going to be my motivating example, and it's also exactly what Ramanujan looked at in this 1916 paper. Okay, so let me start with just a basic definition. Though I mean I don't think Ramanujan kind of thought about the delta function perhaps as a modular form, right? He just looked at it kind of formally, perhaps as coming from some generating series. but from another point of view, certainly it is a modular form. So let me start by talking about modular form, right? So you can look at the space of modular forms of weight k, of some integer weight k, let's say bigger than or equal to 0 or something, and level 1. So in the sense they are modular forms for the full modular group SL2Z, which acts upon the upper half plane by Mobius transformations. Z goes to AZ plus B and upon CZ plus D. The matrix is A, B, C, D. And these modular forms have a Fourier expansion, right, as we were talking about yesterday as well. So they have this Fourier expansion, so that kind of captures the symmetry Z goes to Z plus 1. And then there's this other more subtle symmetry, which is Mobius inversion. So under Mobius inversion, they have this transformation formula, which is kind of very important. So f of minus 1 upon Z is Z to the k times f of C, right? So this k is kind of the weight of the modular form. Okay, so this turns out to be a finite dimensional, so you can look at all these modular forms together and they form a vector space, finite dimensional vector space. And there are 4 formulas about the dimensions of these vector spaces. Okay, so in particular, because these two elements, these two kind of symmetries, Z goes to Z plus 1 and Z goes to minus 1 upon Z, generate the action of SL2Z on the upper half plane. Somehow you get this more, transformation formula under the Mobius action of SL2Z on the upper half plane, right? And now within this space of modular forms, we consider this typically co-dimension 1 subspace, where you kind of look at the subspace for which the constant term is 0, right? So that's the space of cusp forms. So that's typically of co-dimension 1. Sometimes it might be the same, it might be, yeah. We see easily that this space of modular forms vanishes unless k is bigger than or equal to 0 and is an even integer, right? So somehow there's a parity thing which is coming in here, which plays a role in the formulation of Serre's conjecture. It's only some certain kinds of Galois representations which are accessible via using modular forms, and these are the so-called odd representations. And that parity constraint is already seen, and there's the fact that this space of modular forms is empty, is 0 if the weight is odd, right? And then you have for when k is sufficiently large and k is bigger than or equal to 4, then the space of modular forms of weight k, at least 4, is always non-empty, right? So somehow, and there is a certain so there's always some for this range of integers, you can always write down by some sort of averaging process. You want to have some complex analytic function which is invariant under some symmetry, so you can look at some sort of averaging kind of thing. But you can write down as this Eisenstein series of weight k, right, which has this explicit Fourier expansion where all the Fourier coefficients except the first one, except the constant term, is somehow some simple arithmetic function. It's a summation k minus 1 n qn, right, where the summation k minus 1 n is just the sum of divisors of n to the power k minus 1. On the other hand, the Fourier coefficient, the constant term is more mysterious, right? Though it's explicit, it's related to the kth Bernoulli number, but it's some zeta value, right? And somehow it has more deeper arithmetic significance. So the constant term is more mysterious in some ways, or has deeper ties to arithmetic than the more simple-minded arithmetic than the other Fourier coefficients, right? So somehow this interplay between the interest of the constant term and the fact that the non-constant terms that are the simple is also plays a significant role in the subject. Okay, so so you can always write down this one modular form of weight k, and the constant term is non-zero, so it's not a cusp form. Okay, then you can normalize this thing to so that the constant term is 1, and then we call that ek, right? And then these particular things E4 and E6, right, of weight 4 and 6 play a role in the space theory of modular forms of weight of level 1. And these also played a role in Ramanujan's paper, and they were called by him Q and R, right? And the space of modular forms decomposes as the line spanned by the Eisenstein series, and the complementary subspace given by the space of cusp forms, right? So that's kind of the structure of this complex and space of complex analytic functions. All right. So now the cusp forms are more mysterious. Okay, and what you can also do is look at the totality of all modular forms of level 1. You can put them all into some sort of direct sum of vector spaces where all weights k, and then this is some sort of graded algebra. So it's a polynomial algebra in these two Eisenstein series, Q and R, E4 and E6, and it's a graded algebra if you give these Q and R weights 4 and 6, right? And then somehow there are some sort of one can compute the dimension of MK as a vector space over C, and the dimension is roughly k by 12, right? So somehow this grows systematically with k, and one understands linearly with K. And the space of cusp forms vanishes for a larger range of weights than the space of modular forms. So the first time you get a non-zero cusp form is in weight 12, right? So for weight less than or equal to 10, there is no cusp form. And for weight 12, it's one-dimensional, and it's spanned by this delta function, right? Where this is because of Ramanujan's study of it from 1916, perhaps it's called the Ramanujan delta function. Yeah. So now this is the first time of this model space of cusp forms is non-empty. It's the first example of a cusp form. So sometimes whenever you have something which shows up for the first time, perhaps it kind of immediately interesting, and it is quite a remarkable kind of. Okay, so delta function, of course, was studied even earlier than Ramanujan. It was studied by Jacobi and so on, and its connection with elliptic curves. It is related to discriminants of elliptic curves. So Ramanujan's remarkable insights in this 1916 paper into the arithmetic with Fourier coefficients made it maybe that's why it's named after him, right? So let me look at the. So okay, so this cusp form explicitly in terms of this, so it's going to be a weight 12 form, right? So given the weights Q of Q and R to be 4 and 6, so it's some kind of homogeneous polynomial of degree 12 in Q and R, in this particular polynomial Q cubed minus R squared upon 1728, right? And it has this kind of Q product expansion, which is known to Jacobi, right? So Q, it has this product expansion, Q times 1 minus Qn to the 24, and then we can expand it out, and it has a Fourier series, and by definition, you call the Fourier coefficients the tau function, right? So it's called summation tau n Qn, and it's the normalized cusp form of weight 12, right? With the coefficient of Q equal to 1, and that has no constant term. It is a cusp form. Okay, so now these for Ramanujan, perhaps I think the delta function was primarily given by this product expansion, right, rather than the connection with modular forms. So, but of course, I think perhaps with his remarkable intuition, he perhaps knew that this function was very important, and it is the Fourier coefficients are called the Ramanujan tau function, and Ramanujan conjectured like 3 properties about this tau function, right? So he conjectured some multiplicativity property of tau, which is the tau mn, when mn and a coprime is tau m times tau n. Then he conjectured a recursive formula for tau evaluated at powers of p. So it's not completely multiplicative, because then it would be perhaps not so interesting. But I mean, okay, so the tau p to the n plus 1 has this formula, right? It is multiplicative up to some compensation, up to some error. Not exactly multiplicative. Tau pn times tau p, but then there's a correction of to subtract from it p to the 11, where 11 is 12 minus 1 times tau p to the n minus 1. Right? So he conjectured these 2 properties of the tau function. And then the third thing, which turned out to be the deepest property, is that the size of tau p is less than or equal to 2 times p to the 5.5, right? So 2p to p to the 11 upon 2. So these are the 3 things he conjectured in this paper. He didn't prove it, but he conjectured them. And you find this table in Ramanujan's paper, right? He just tabulates tau for 30 values of n. So they're growing pretty fast, right? Already, when you get to tau of 30, it's some 2 million something. Yeah. So it's kind of growing rapidly. So he computed presumably by hand, of course. And just looking at these, or looking at more values which he didn't write down in this table, he conjectured these things. Right? There's some table 5 of this 1916 paper. And he made these kind of remarkable conjectures on the basis of these 30 values, which he wrote down, or perhaps more values he computed and did not include in the paper. And here's a picture of him. Okay, and the first 2 statements were actually proven rapidly soon after he conjectured them, and they were proved by Model. And so for doing that, somehow he defined operators Tn, which came from some sort of fact that you can think of modular forms as functions on lattices, and then you can changes. You can use some averaging operator, right? So the way Model proved this was by kind of realizing these tau n's as eigenvalues for certain operators, which he defined, and which were later called Hecke operators, because Hecke studied them more systematically. But they were introduced in this particular context of weight level 1 modular forms by Model, right? And he introduced these operators, and these operators had somehow more meaning than just being sort of defined by some, like unlike tau n, which initially could be thought of as being defined combinatorially. They had some meaning in terms of the interpretation of modular forms as maybe functions on lattices and so on. So using that interpretation, one can define some sort of averaging operator, right? Well, when you sum over the values of this modular form on lattices of index n or something. So you can define some operators on the space of modular forms, and they are commuting set of operators. They also preserve some inner product. So they're self-adjoint and they can be diagonalized, right? So this is in general what you have. So these are not only complex vector spaces, but they have these operators, diagonalizable family of operators. And using this interpretation, this meaning of these operators, one can sort of prove for these operators the formulas Ramanujan had conjectured for the tau function, right? So there's multiplicativity of tau, of these Hecke of these operators. Tmn is equal to Tms times Tn for Mn and co-prime, and T of p to the n plus 1 again has the same formula, sort of formula as Ramanujan had conjectured for tau p of n, tau p to the n. Right. So somehow the proof of the first first two things which Ramanujan conjectured was just again, this is not clicking. Okay, and then the connection again with the Fourier coefficient. If you have a cusp form which is an eigenform for all the Tn's, then first of all the first Fourier coefficient doesn't vanish, and if we can then divide it, normalize it to be 1, because that doesn't change eigenvalues, then there's a connection between the eigenvalues and Fourier coefficients, right? So for an eigenform which is normalized so that the constant term, so the coefficient of Q is 1, then there's a direct connection between the eigenvalue of Tn and the nth Hecke operator and Fourier coefficient of f. Right? So f of Tn is equal to an of times f. And there's because I said these operators can be diagonalized, there is a basis of eigenforms, right, for this for these operators. On the space of cusp forms, these operators preserve the space of cusp forms. They act upon the total space of modular forms, and these Eisenstein series I wrote down are Hecke eigenforms for Tn, and the eigenvalues are exactly this simple arithmetical function, summation d to the k minus 1, where d divides n, k minus 1, right? So this is a story of modular forms and Hecke operators. And now, of course, the Ramanujan conjecture, these first two conjectures follows, right? And okay, if you want an explicit formula in terms of Fourier coefficients for L prime, it has some sort of nice shape. F of TL, F applied to the L Hecke operator has this kind of shape. And now, as delta is the unique cusp form of A12, it is and these operators commute, it is an eigenform for these, it is an eigenform for the operators, right? And it is normalized. Delta is, it has the first Fourier coefficient to be 1. So the delta function is indeed an eigenform for these Hecke operators with eigenvalue tau n, right, which are the Fourier coefficients of delta. And because TL satisfy these multiplicatory properties, so do the eigenvalues, right? So that's how Model proved these conjectures by giving some meaning to the Fourier coefficients as eigenvalues of operators, right? And the operators satisfied those sort of multiplicative properties which Ramanujan had conjectured for his tau function, right? So in some sense, if you want to use some sort of anachronistic language terminology, this is some idea of categorification, right? You instead of looking at numbers, you interpret them as eigenvalues and prove properties about these operators, and hence deduce properties of eigenvalues, right? So that was the strategy of the Model's proof of these first two conjectures. Yeah, but I think Hecke studied them more systematically, and but in the case of level 1, it was introduced by Model. Yeah. Exact history. Yeah. But certainly Hecke made a deep study of it in the next decades. Okay, so this is the strategy of the proof of Model, that you realize tau n's as eigenvalues of these operators, for which you know the relations which Ramanujan had conjectured for these eigenvalues. Right? Any questions? Okay, now the other thing actually, so the Ramanujan, I think, was aware of this connection, that the things he was writing down, the first two properties, that tau mn is equal to tau m times tau n, and tau of p to the n plus 1 is tau p times tau n minus p to the 11 times something times tau to the pn minus 1, right? So this is somehow equivalent to the fact that if you look at the kind of this Dirichlet L series attached to delta, right? Formally, you can just write this down, tau n upon n to the s. Then this is equivalent to the Euler product expansion, that is equivalent to the delta function, have L delta S having a Euler product expansion, right? Similar to the Riemann zeta function, for example, or the Dirichlet L function, but somehow the Euler factor is kind of more complicated at P, right? It's of degree 2, right? So okay, for example, for these Hecke, for example, for these the delta function, L delta S proved the functional equation for this completed L function. You tag on some factor at infinity, 2 pi to the minus S times the gamma function. Right, and he proved this as a functional equation as a consequence of this Mobius inversion, this more subtle symmetry which the space of modular forms has. Okay, so but Ramanujan, I think, was aware that this whatever he was conjecturing was equivalent, at least formally, to this delta function having this Euler product expansion. Right, so in some sense, I think this is the first appearance in the literature of Euler of an L function with a degree 2 product Euler expansion. Right, so for example, if you in some sense the Euler the Euler factor at P is kind of degree 2 is related to degree 2 polynomial 1 minus tau p x plus x squared, right? If you put x equal plus p to the L times x squared, if you put x to the p be p to the minus s. Right? So typically in the Dirichlet function, you just get something like 1 minus chi p upon p to the minus s. So it's a degree 1 Euler product expansion. There's a degree 2 Euler product expansion, maybe related to the fact this is a function with some symmetry on like 2 by 2 matrices. Yeah, so I think maybe this is the first appearance in the literature of a L function with a degree 2 Euler product. Okay, now so this took care with pretty so the Ramanujan first two of Ramanujan's conjectures were proved by mod L pretty within the, I don't know, very quickly after he made them, right? But the third property, right, which was this kind of thing, this very weird thing about tau p being 2 times p to the 11 by 2, which, right, some fraction p to some fraction. It turned out to take much longer, right? If you want to have some sort of almost as good bound, but not this optimal bound, if you want to say it's bounded by something like p to the 6, then the proof is very easy, right? You can give a very easy complex analytic proof using some maximum modulus principle. And in fact, when I think Hardy lectured on Ramanujan, I think some lecture that, yeah, there's some book of Hardy's lectures on Ramanujan. He was slightly skeptical about the importance of this sharpening that Ramanujan conjectured, right? And this sharpening was conjectured by Ramanujan on the basis of these 30 values of tau n he had computed. So it must, I think it took remarkable intuition to somehow see that the answer should be p to the conjectured answer should be p to the 5.5 rather than p to the 6. So he said that maybe because this bound, this conjecture, this third conjecture, Ramanujan seems to be like a kind of, we seem to have drifted into one of the backwaters of mathematics. But of course, Hardy did qualify this remark, so he's kind of, by saying that the problem might have some features which made it not unworthy of Ramanujan's attention, right? So, but maybe he himself, sorry. Yeah. He himself perhaps didn't see what the point of it was, but maybe because Ramanujan was someone with some, Hardy respected Ramanujan and his intuition, maybe decided to give it some possible importance, which Ramanujan saw and he didn't see. Anyway, but this conjecture has actually turned out to be tremendously important, and it's like the first case of a series of conjectures, which kind of is one of the central problems driving the theory of automorphic forms. Right? And there's a large complex of conjectures which are called Ramanujan conjectures, and these are conjectures about eigenspectral, I mean, about the spectral eigenvalues of Hecke operators in the space of automorphic forms in great generality, and there are many cases which are unknown of this conjecture, of this generalized Ramanujan conjecture. All right, any questions so far? All right, and there's another thing this time he did not, I think perhaps proved it, or I mean, this is something he also observed, that there's a congruence for tau n, right? There's the tau n, right, which is a kind of complicated function. It grows very rapidly with n, but it's related to this much simpler function, which is just the sum of divisors function, right? Sigma 11n mod 691, right? So the 691 is kind of a pretty large prime, right? So it's kind of an impressive looking congruence. And the 691 somehow has one significance in terms of it, because it's, perhaps that's the way this kind of congruence is proved, is that the 691 divides the numerator of B12, right? The 12th Bernoulli number. And somehow, if you remember this GK, this Eisenstein series of weight 12 unnormalized, its constant term is minus BK upon 2K, right? So minus B12 upon 24. In this case, 691 divides the numerator of B12, and therefore mod 691, right? If you can just formally remove, look at the Fourier coefficient mod 691 of this weight 12 Eisenstein series, the constant term disappears, right? So mod 691, it kind of looks like a cusp form. And on the other end, there's a unique cusp form of weight 12, which is the Ramanujan delta function, whose Fourier coefficients are tau n. Right? So maybe you can make a heuristic case that this kind of congruence should be true, because mod 691, this space of Eisenstein series looks like a cusp form, and there's a unique cusp form, which is the delta function. Anyway, so along these lines, one can prove this kind of congruence, that tau n is congruent to sigma 11n mod 691. So somehow 691, of course, is a very famous prime in the subject because of its appearance in this setting, as observed by Ramanujan. Okay, so these congruences especially played a big role in the development of the theory of P modular forms, and which then led to Serre's modularity conjecture. Now, after Ramanujan, I think there was a series of some similar observations about such congruences made modulo different primes, right? 691 is the most impressive of the primes, because it's the largest prime, but there were other such congruences made modulo. Somehow it's always that the tau n is congruent modulo L for one of these L's, except 23, to some divisor function, right? So for L equal to these, how many? 1, 2, 3, 6 primes, 2, 3, 5, 7, 23, 691. Following Ramanujan, people observed congruences for tau n mod L for these 6 primes, right? 2, 3, 5, 7, 23, 691, and these are called exceptional primes in this setting. And the point about these congruences perhaps is that these the tau n is quite complicated function. There's no simple formula for it, but modulo these primes somehow it degenerates, right? And there's a simple formula for it. So, and then in some sense, one of the things which Serre and Swinnerton-Dyer explained in the 1960s is why are there congruences for such primes and why are there no other congruences? And no one ever found congruences for anything except these primes, right? So they've tried to kind of undertake a study of more systematic algebraic geometric study of mod P modular forms, which would explain this phenomena of why are there no more congruences other than these primes, right? So for the explanation for these congruences given by Ramanujan, given by Serre and Swinnerton-Dyer, and the Ramanujan bound, which was proved by Deligne later in the 1970s, lay in some sort of the Galois representations which arose from the which attached to delta. And I think perhaps Serre, who kind of made this connection that perhaps some of these things should be thought of in terms of some Galois representation, which should be associated to delta, right? So he conjectured in this Delange-Pissot-Poitou seminar in 1967 or 68. He conjectured there should exist a Galois representation rho delta L from the absolute Galois group of Q into GL2 of the L-adic numbers, which should be irreducible and unramified outside L, right? So somehow this, and the fact that it's supposed to be unramified outside L is related to the fact that delta is a modular form of level 1, right? It's a modular form for the full congruence, for the full modular group SL2Z, right? And this representation was, he conjectured this to exist. I mean, of course, this conjecture was not out of the blue because such Galois representations were known to exist for modular forms of weight 2. So some of the extra feature, he was conjecturing them for higher weight bigger than equal to 2, for example, weight 12. And this representation is characterized again by telling you what happens at for these representations that marked conjugacy classes of this Galois group, which indexed by primes, the Frobenius classes, Frobenius of P, and then this representation is determined by the Cherenkov density theorem by telling you by saying that by conjecturing that this rho delta L of Frobenius evaluated at this conjugacy class, the characteristic polynomial should be this Euler factor which showed up in the Euler product expansion of L delta S, right? So, or something related to that. So the characteristic polynomial is x squared minus tau px, the tau p being the Ramanujan tau function at p, plus p to the 11, right? 11 being 12 minus 1. Okay, so this, and 12 being the weight of the delta function. So this was conjectured by Serre, and again, this conjecture, once he made it, was proved, okay. So as I said, this was not out of the blue. I mean, such representations attached to modular forms of higher level, but weight 2, or all levels rather, had been constructed by Eichler and Shimura, right? And somehow he was just said that this some kind of thing should exist for them. And in that case, somehow the construction it's related to abelian variety, so it was somehow. No, the fact that it's of higher weight, that's bigger. Yeah, weight 2. These constructions of Eichler Shimura were in weight 2. Somehow you have to use non-trivial, you can't just use constant coefficients in the homology. Again, the proof of the Ramanujan conjecture was an instance of what I'm trying to call categorification, right? So I have to interpret these numbers tau p in a more sophisticated way. You can't just work with them as Fourier coefficients or given by this product expansion. So, so the way Deligne proved this was by, for example, first proving that Serre's conjecture is right, and there is indeed a L-adic representation. So Deligne, soon after Serre conjectured this representation to exist, Deligne proved it existed. So that was soon after, and then he realized these Galois representations which Serre had conjectured to exist. He proved they exist, and they arose in some geometric way, right? And some from the étale cohomology of the J line, with some system of some sort of sheaves, right? Okay, and he interpreted tau p as a trace of Frobenius at p acting upon this cohomology group. Okay, I'm not going to go. I just wanted to mention. Should I be responding? I don't know the question.
I think if you can repeat the question of Chantal.
The difficulty of Serre, I think Chantal asked what was the difficulty in proving Serre's. Yeah, because somehow, I mean, it's not realized via abelian varieties or via looking at H1 with the trivial coefficient. You have to look at some sort of non-constant sheaves. Yeah. So some of the weight was the difficulty. The fact that the weight was bigger than 2, weight 12, right? And so okay, so the way Deligne kind of proved this conjecture of Ramanujan, maybe 6 decades or so, roughly 6 decades after Ramanujan conjectured this, was by this process of first interpreting tau p as coming from the action of Frobenius on some étale cohomology. So interpreting this tau p as a trace of Frobenius in some L-adic representation. And then he proved the wave conjectures for these kind of cohomology groups, and hence deduced the Ramanujan conjecture. Right? So it was a very long, deep story of needed Grothendieck and his school to develop the theory of étale cohomology, and it was a very long road. Very important mathematics was done en route to it. And yeah, so that's how Ramanujan's this Ramanujan bound was deduced, right? And then Hardy was right, or Ramanujan was right, and kind of latching onto this. It turned out to be of great significance to try and prove this conjecture. Yeah, so it should be k minus. In general, the weight k forms will require sim k minus 2 of ZLs of the two-dimensional vector space of QN lattice. There was maybe some. Again, there was some maybe work of Kuga and Shimura or something. But yeah, but it was in the air, but okay, Serre conjectured it, and it was rapidly proven by Delhi in terms of at least the existence of these Galois representations. It took another 5 years for Delhi to prove the wave conjectures, and hence deduce that tau p satisfied these bounds. Okay, and so Serre conjectured that these tauins kind of had this interpretation in terms of trace of Frobenius, and of course, once you kind of corral all these tauins into this very kind of smallish Galois representation, GL to ZL, right? It's somehow forcing some. They can't be like random. There's some sort of extra symmetries they acquire. So maybe to kind of one has to be sure that one really thinks that these things could exist, and I think perhaps Serre writes it in that seminar where he formulated this conjecture about existence of Galois representation. The fact that Swinnerton-Dyer had shown, because somehow Serre and Swinnerton-Dyer, even without knowing the representation existed, decided to just assume it exists and analyze it, right? Once you say such a representation exists and has such traces of, and has such characteristic polynomials, it is embarked on studying it, right? So for example, Swinnerton-Dyer then proved that if such a representation exists, then the image of this two-adic representation, as well as the delta function, right? He could completely characterize what it is. Right? He could characterize it's a subgroup of GL to Z2 of some very large index, right? And this congruence somehow, this thing then explains some other known congruence of for the tau function mod 2 to the 11, right? Lamer had written down this congruence, right? Some kind of somewhat involved congruence, and the fact that somehow the Galois representation and the fact that its image then controlled explained certain rather exotic looking congruences was in evidence that these representations should exist. Okay, but anyway, they were rapidly proven to exist by Delhi. Okay, now how does one, for example, explain the modern 691 congruence of Ramanujan? The fact is that the 691 adic representation, right, is irreducible. I mean, Serre had probably proven that in this Delonge, it's certainly true that this representation in characteristic 0, the 691 adic representation is irreducible, but this extra congruence that this congruence tau n has mod 691, the Galois theoretically is basically the phenomena that when you reduce this representation mod 691, somehow it becomes reducible, right? So an irreducible representation becomes reducible, and in fact, it has this particular shape. It's the Galois sigma. I mean, the Galois representation is up to semi-simplification is the sum of two characters, the trivial character, and the 11th power of the mod 691 cyclotomic character, right? The character which gives you the action of Galois on 691's first roots of unity. Right? So somehow then the congruence had this meaning that this representation became reducible mod 691 and had this particular shape. Okay, and as I said, I mean, Serre and Swinnerton-Dyer kind of even perhaps not without knowing, without waiting for them to prove the conjecture, they already started studying the image, right? And they proved that they could somehow they could say that this representation, the L-adic representation associated to the delta function, and whose tie-up with the delta function is via the characteristic polynomials of the Frobenius elements in this representation. The image contained SL2ZL for all L different from these exceptional set of 6 primes, right? For all L not equal to 2, 3, 5, 7, 23, 691, this representation contains SL2ZL. Right, and for this they use some kind of nice group theoretic lemma, right, which reduced the problem to showing how large the mod L image was, right? So some kind of Nakayama's lemma in this setting. They show that if you want to show that the L-adic representation is large, it's enough to show that the mod L image is large, right? It contains SL2FL, at least for L bigger than 3. Okay, so they proved this simple group theoretic lemma. But and then some sense to prove these image theorems, one had to really understand the mod L Galois representation. This led them, maybe I might skip this slide. This led them to studying the theory of mod L modular forms. Right, so they kind of undertook maybe I'm going to skip this. They undertook a study of these mod L modular forms, really thought about them geometrically, right? Because you define the space of mod L modular forms just by choosing an integral basis of the space of modular forms of level 1 of weight k and just reducing integral in terms of the Fourier expansion, in terms of the Q expansion, and just reducing the space of characteristic 0 forms mod L, just reducing the Fourier coefficient mod L, right? So that's a mod L modular form. You just reduce the most kind of a naive definition of what a mod L modular form is. And then somehow they observed that the space of mod L modular forms have these extra operators, right? Kind of this multiplication by the Hasse invariant. And they have some extra structure that the space of complex modular forms doesn't have. They also use an operator which actually had been studied by Ramanujan, the QD by DQ operator, right? Which plays a significant role in this theory, which just sends summation AN QN to N times AN QN. Okay, and so somehow they kind of developed some theory which helped them to show that the image of the Galois representation mod L, or rho delta L mod L, for L not equal to these 6 primes, contains SL to FL. Right? So somehow the geometric the geometric theory of mod L modular forms they developed led to their theorems about the images of Galois representation. They started a systematic study of congruences between modular forms, right? So for example, here's a congruence which I think Swinnerton-Dyer probably observed. So if you look at the delta function, which is a weight 12 modular form of level 1, you can do some Fermat's little theorem kind of manipulation, right? You can write 1 minus qn24 as 1 minus qn squared times 1 minus qn to the 22. Use the form, and then mod 11, you can put the 11 inside somehow by just by the binomial theorem or something. And you get another Q expansion, Q to the product 1 minus Qn squared times product 1 minus Q11n squared, right? Mod 11. And this one can recognize to be a modular form as the kind of Q expansion or the Q product expansion of the modular form of weight 2 and level 11. Right? So there's an exchange between weight 12 and weight 2 and level 1 and level 11. Right? So at the cost of increasing the level from 1 to 11, you can lower the weight. Right, and this also turned out to be a special case of some general phenomena. Right, Serre later proved that there's a Hecke equivariant isomorphism between the, and all these kind of things play a role in Serre's conjecture, right, in trying to define weights and all that. So this kind of formal manipulation, which one can do by Fermat's little theorem, can be systematized and actually say that for all L, there's a isomorphism between the space of modular forms of weight L plus 1 for a prime L. And level 1, and the space of modular forms of weight 2 and gamma naught L, but mod L, everything mod L, so with FL coefficients. Yeah, so this is another way of, no, here I'm not talking, I'm just talking about a congruence just at the level of Fourier coefficients of modular forms. There's no Galois representation, right? And it's just doing some manipulation and saying that delta can be made to look, looking at the mod L reduction of the space of modular forms of weight 2 and level L. Yeah, so there's some exchange phenomena between the weight and the level, yeah, which is kind of explains the Ramanujan, this formal congruence, because for L equal to 12, you get S12 SL2Z, which is FL, which is basically spanned by the delta function model. And then S2 gamma naught 11 is exactly spanned by, it comes from this, it comes from some modular form of weight 2 and level 11. It gives rise to this elliptic curve conductor 11 and one of the two. And it explains more systematically this formal manipulation, right? So this is not just a formal manipulation; it's a general phenomena for all prime. So let me just recall. I mean, so the results Serre and Swinnerton-Dyer proved were that rho delta L, for example, this L-adic representation is irreducible and is odd, right? This oddness is very important, and it's tied to the fact that the weight of the modular form in general of modulus in level 1 are always even, right? If the weight is odd, there is no modular form; it's 0. I mean, the space is 0. So related to that, the fact that this representation is odd, which is to say, if you look at rho delta L evaluated at complex conjugation, right? A complex conjugation is some element of some conjugacy, well-defined conjugacy class of the absolute Galois group of Q. Then when you evaluate rho delta L at complex conjugation, the image has to be of order 2, and it's never a scalar. It's always a regular element. The eigenvalues are 1 and minus 1. Right? And that's related to this parity thing which you saw for modular forms, that the weights are always even in level 1. And the other, okay, so they proved this, and then by their kind of study of the deep study of modular forms of mod L, they proved that the reduction of this L-adic representation, if it existed, which was then proven to exist, mod L is absolutely irreducible. And for L not equal to, let me jump to the last thing, and for L not equal to these exceptional primes, in fact, not only is the mod L image irreducible, but the image is very large, right? It's very non-solvable, for example. It contains SL2FL. And for L equal to 23, there was some particular phenomena which happened, which I'm not going to stress too much. And though it is this, it is related to the splitting field of this famous polynomial x cubed minus x minus 1. And the determinant of this Galois representation is kind of okay. That was it's so easy to prove that if you accept the characteristic polynomial of Frobenius and the shape, that the determinant of this representation is the 11th power of the mod L cyclotomic character. Right. So some of the deepest power, I mean, perhaps what required perhaps the most work is showing this last thing, that the image is in fact pretty large for most primes L outside this exceptional set. Right. So they come and showed this. And using this, okay, again, I'll just using this, they could somehow then just explain the fact that that Ramanujan delta function, tau function, has no congruences modulo, no simple-minded congruences, which related to like sums of divisors type of things, outside this set of exceptional primes. Right? Because the image somehow is non-solvable for L not equal to these primes. It's incompatible with tau and having some simple congruence model. Right? So they found a group theoretic explanation for why these congruences did not, these were the only primes for which, with respect to which you could find congruences. And for those primes, people had found congruences. Right? So it gave a completely sort of a clean answer to why these congruences existed for these, did not exist for primes outside the set. Right? Because the image of the mod L Galois representation coming from the delta function is non-solvable. Right? Because it contains SL to FL, which for L bigger than 3 is non-solvable. Right? So somehow they found some kind of Galois theoretic way of explaining these, why these were the only congruences. Okay, so now I want to tell you that how this kind of thing can lead to trying to look at the converse question. You're going from rho delta to rho delta L bar. How can you, given a rho bar, how can you say it comes from delta? Right? So some of the Serre's modularity conjecture is a converse to the construction of Galois representations he had attached or conjectured to be attached to the delta function. So now let's look at the splitting field of this mod L Galois representation, right? So the fixed field of the kernel of this representation. So the properties of this split, just field theoretic properties of this splitting field of this rho bar delta L, which is the Galois group of the Galois extension through which this representation factors, is that K delta L is unramified outside L in infinity. Its Galois group is kind of a subgroup of GL to FL, and it's typically contains SL to FL. If outside this exceptional set, the Galois group contains SL to FL. This representation somehow is ramified at infinity, which is basically some property of the oddness of this representation. And somehow there's also a further fine property, which I'm kind of now, again, ahistorically perhaps conjecture, because I think when Serre and Swinnerton-Dyer wrote down this stuff, they did not perhaps know this last fifth property. Okay, so these representations are unramified outside L in infinity. So but one would like to understand what's happening at L, right? What is the shape of inertia? How ramified are they at L? So then somehow there's some answer that that either so if you look at the mod L Galois representation, when you evaluate it on decomposition group at L or inertia at L, then it is one of the two shapes. It's either the identity character plus the 11th power of the mod L cyclotomic character, right? Or it is something else, which I'm not. It is the sum of two characters, which are called fundamental characters of level 2. Right, so somehow there are two possible. Somehow this was conjectured but maybe this was guessed by Serre, and this was proven again within a few years. I don't know exactly by Deline in the first case and by Fontaine in the second case. In fact, Serre Fontaine I think Serre proposed to Fontaine these questions, whether he could analyze the mod L Galois representations, and somehow the behavior at inertia at L is related to how tau L looks mod L. Right, as I say in the next slide. So these two behaviors of inertia at L these two behaviors at inertia at L of the Galois representation of the splitting field of the Galois representation rho delta L bar are related to how tau L behaves mod L. Right, the first case of when it's a direct sum of the identity and the cyclotomic character, the 11th, the first case is equivalent by results of Deline and Fontaine to saying that L does not divide tau L. Right? And this is typically one. I mean, this is a situation again. One doesn't know whether it happens. What happens for primes? Whether this happens infinitely often, or the converse. Whether L divides tau, one of the two is going to happen infinitely often, but you don't know which. Either L divides tau L for infinitely many L, or L does not divide tau L for infinitely many L. You don't know which direction it is. On the other hand, experimentally, it's very rare for L to divide tau L. Right. So, for example, L does not divide tau L for all primes less than 7 million. Or 7, is it million? Yeah. And L not equal to 2, 3, 5, 7, and this large prime to 2411, right? So I think when Serre wrote this, they launched piece of Poitou paper, he did not perhaps include the prime 2411. And then the solutions up to 10, 10 to the 10 to the equation tau L to the congruent to 0 mod L. The only solutions are 2, 3, 5, 7, 2, 4, 1, 1, and then this very frighteningly large prime. Okay, right, which is 7 billion, I think. Okay, and something. Right, and okay, the other related conjecture here, which is about characteristic zero properties of tau L, right? This is a conjecture about tau L mod L, not conjecture. The phenomena of tau L mod L, and then it's whether it's zero mod L or not zero mod L has some Galois theoretic consequences on the inertial behavior of rho delta L at L. Yeah, and so this say Lehmann has made this conjecture that tau N is never also zero. Okay, and again that's not known. Right, so these are some sort of again some numerical properties of tau L and the Galois theoretic interpretation. Okay, so so the first version of Serre's conjecture. So Serre made this conjecture in a letter of Serre to Tate in 1973. He made some conjecture, which kind of was a converse to his going from a modular form to a mod L Galois representation. He tried to conjecture which Galois representations arise from level 1 modular forms. Right. So a rough version of Serre's conjecture would ask that any extension K over Q, which verifies these properties which I wrote down for K delta L, the splitting field of delta mod L. Right? Anything which satisfies such properties should come from the delta. It should be K delta L. Right? So it's a converse to the construction of mod L Galois representations associated with delta functions. So this is a picture of Serre. And in some sense, this was the first case which Jean-Pierre Mathematiques and I proved when we proved Serre's conjecture. Right? So some of the delta okay. So I'll tell you the more formal version of Serre's conjecture in a minute. But it's anyway a converse question to. Okay, and the fact that so if we drop information about exactly the ramification behavior at L of these extensions and just say it's unramified outside L in infinity and all that other properties, then the conjecture would say that the splitting field, the K arises for the splitting field of the mod L Galois representation associated to some eigenform, Hecke eigenform of level 1, right? And then the weight will depend upon how the inertial behavior at L looks like. And then when we further drop the condition that is unramified at outside L in infinity or allow auxiliary ramification, then you get the connection to higher level modular forms. Right? So the Serre's conjecture is about fields, extensions of Q, whose Galois extension of Q, whose Galois group is something like GL2FL, which are kind of ramified at infinity. So some of the odd representation or the projective representation should be ramified at infinity. And yeah, then it kind of tells you that all such GL2 kind of FL extensions or FL bar extensions should come from modular forms. Right, so somehow it's a converse question. I'll tell you exactly the conjecture in a second. Right, any questions so far? So example, so if you look at L equal to 11, right, then Serre is conjecturing that if you have a representation into GL to F11 unramified outside 11 and the conditions on inertia at 11, it should have a particular shape on inertia, then Serre predicts that it should come from a weight 12 modular form, or alternatively, it should come from the elliptic curve of conductor 11, where there are two of them up to isogeny. So it should come from the Levin torsion of the elliptic curve, one of the elliptic curves of conductor 11. And this curve is this explicit curve, right? So the mod 11 representations coming from delta and this curve coincide by this formal manipulation I told you about, right? This Swinnerton-Dyer. Okay, so in this context, yeah, the Ramanujan conjecture has some delta function as another significance, which I'll skip. Okay, so let me officially formulate Serre's conjecture. So it asserts that if you have any representation of the absolute Galois group of Q into GL2 of a finite field of characteristic L, and as long as it's continuous, as long as it factors through some finite Galois extension and is odd in the sense the image of complex conjugation is not a scalar, then they should arise from the kind of construction Serre from Galois representations associated to new forms of some weight and some level, and that weight and level were made specific in Serre's conjecture in his Duke paper in 1986. Yeah, but that's in level 1. Yeah, in higher. Yes. Yeah. Yeah. Yes. Yeah. The space of odd representations is explained by the space of modular form. The weight may not always be odd in higher level, but yeah, there's some parity constraint. Yeah, but I think if you look at some other weights, I mean, maybe odd weights, but then you can compensate by having some Nebenthal types. Yeah, so it's some phenomena of what, yeah, it need not, the weight need not be odd, but the representations arising from rho are always odd. It's basically the fact that the modular form is going to be invariant under the matrix, maybe -1, 0, 0, -1, right? Which acts trivial in the upper half plane. So there's some parity constraint coming from there. Yeah, it's some easy thing. Yeah. The converse is more difficult. I mean, so any representation you hope to come from modular forms has to be odd, but except for L equal to 2 and there's no constraint, when everything is odd. Yeah, So this is the conjecture of Serre, that abstract mod L Galois representation into GL2 of a finite field, which are odd and irreducible, come from modular forms. Right? So purely Galois theoretic objects can be you can characterize those which come from modular forms just by imposing oddness. Capital F, or little f? F, okay, this F is a finite field of characteristic, any finite field of characteristic L. Or you can look at FL bar, for example. Yeah, but look at all of it. So somehow, I mean, yeah, I think so. Serre in this 1986 paper, he writes down this conjecture and makes a series of deductions, one of which is the modularity of elliptic curves. Yeah. Because you have to apply this conjecture for infinitely many primes. Yeah, not one prime. Yeah. Somehow I think this was an observation of Colmez, that you can use his conjecture of Serre to prove characteristic zero statements, like which predated Serre's conjecture. Yeah, so somehow this is a statement that any abstract Galois representation or Galois extension with certain Galois groups come from modular forms, right? So somehow it's a converse to the construction of Galois representations coming from modular forms. Okay, so somehow, I mean, when Serre first made this conjecture, he did not really specify the optimal weight and level part of the conjecture. He made this he formulated this conjecture to Tate in 1973 in the level 1 case, so when these representations are unramified outside L. And immediately Tate proved this conjecture for L equal to 2, right, in the return post. Right? A beautiful elementary argument using Minkowski's theorem about bounds and discriminants and so on. Tate proved this conjecture for L equal to 2, and then, okay, but then, so Serre formulated this conjecture to Tate in 73, and then he published this in some asterisk volume in 1975. And then he formulated, maybe this should be 1987, anyway, he formulated a more precise form of the conjecture where you really specify the modular data from which rho is supposed to arise, the optimal modular data. In a paper he wrote in the Duke journal dedicated to, I mean, I think for Manin's 60th birthday, perhaps, or 50th birthday. And yeah, where he specified the optimal weight and level, and somehow the stimulus for that to really make precise the invariance from which this representation, abstract representation, should arise in terms of the type of modular form from which it should arise. He wanted to make Frey's observation or intuition that Fermat's last theorem should follow from the modularity conjecture. Right? So somehow he wanted to pin down the mechanism of how to deduce. Yeah. Anyway, so I talked about modularity of elliptic curves over Qs. I'm going to skip over these slides. Pictures of Taniyama, Shimura, and Wei. Okay, and so I think maybe I took this is a picture of Serre from the Lumini conference, and maybe okay. So yeah, so the connection between Fermat's last theorem and Serre's conjecture is that, as explained yesterday as well, that you start with this Fermat's violation, or start with counterexample to Fermat for some exponent prime p. Then you consider the mod p representation arising from this elliptic curve, and then you examine the invariance Serre attaches to this representation. They turn out to be k rho is equal to 2, and the level is 2. So Serre's conjecture, or the refined form, which will actually specify from which space of modular forms it arises, will tell you then that this representation arising from the p torsion of this elliptic curve, which has very limited ramification, should arise from the space of modular forms of weight 2 and level 2. On the other hand, the space is 0, right? So that's some of the contradiction. Because I also, by results of Maser, one knew that this Galois representation is also irreducible, which is an important input into this thing. Right? And Ribet had proved enough of this more precise, enough of he had proved something called the epsilon, whatever. It proved something related to Serre's conjecture enough to deduce this kind of assertion from the modularity. Okay, so Andrew, I'm almost, yeah. So maybe I'm going to finish. So and of course, as you know, Andrew Wiles proved this conjecture of modularity conjecture of elliptic curves in 1994. But okay, so as far as Serre's conjecture goes, which is a mod L version of this kind of statement, it's in some sense a mod L version of the Fontaine-Maser conjecture. It's trying to characterize which mod L representations come from modular forms. So we proved this conjecture in kind of roughly in terms of from the initial idea to writing it down and getting it published. We proved it in this period, 2004-2009, during which I came to Montreal for a conference, which was, I think, about Galois representations. And for example, the conjecture, of course, I mean, though it uses Wiles's techniques, in some ways you can give a proof of, you can give a rearranged proof of Fermat's last theorem, right? Following by showing that this rho EP, which would arise if such a violation of Fermat's last theorem existed. So you show that if you look at the mod P representation, right, arising from this elliptic curve, you know it has I mean, it's unramified outside 2 and P, right? Some of that, and at P it's nice, and at 2 it's kind of semi-stable. So what we showed is, using Wiles's techniques and developments of it, we showed that rho EP arises from a semi-stable abelian variety A over Q, it already arose from an elliptic curve. That was how it arose, right? But you somehow lift it out. You also show it arises from some other object, which is an abelian variety that has good reduction outside 2 and is semi-stable at 2. And on the other hand, Fontaine and Abrushkin, right, using study of p-divisible groups and discriminant bounds of Minkowski or developments of them due to Odlyzko, had shown that no such abelian variety exists. Right? So somehow the one way of thinking about proving Fermat's last theorem is to somehow show that this mod P representation arising from a violation of Fermat's last theorem at exponent P will give rise to an abelian variety with good reduction outside 2 and semi-stable reduction at 2, right? And on the other hand, there is no such abelian variety, non-zero abelian variety. Right? So this was, in fact, I'm told that this was a line of attack on Fermat's last theorem, which had been suggested by Tate. And somehow our strategy, the things we introduce in our proof of Serre's conjecture allow you to prove this kind of strategy. Right? This mod P representation is originally arising from an elliptic curve, which typically has bad reduction at lots of primes. But because its mod P representation is very little ramified, one uses that to lift it to another, to show that it arises from another geometric object, another abelian variety with very limited bad reduction, and that thing is zero. Right? But of course, I mean, this is a rearranged proof of Fermat's last theorem, but certainly the techniques used are heavily dependent on the modularity lifting results of Y. Okay, so now just to okay, so this is John over here. He unfortunately passed away years ago. Okay, I'm going to end. I'm just going to end with one conjecture about one question about counting model Galois representations. Okay, I just take 2 minutes. Right. So one thing which the Serre's conjecture leads you to ask is how many model Galois representations are which are into GQ into GL to FL bar, which are unramified outside L and odd. Right. Okay. Oh, sorry. Okay. So here, let me end with this question, because otherwise I've been talking about a historical thing, but let me end with something which is actually not known even now. So one can ask how many semi-simple Galois representations are there into GL to FL bar that are unramified outside L and odd. Right. And as a corollary of Serre's conjecture, you get that there are finitely many such representations. Okay. So, but the question is how many are there? I mean, at least some estimate or number. So one can kind of make a guess using kind of some philosophy or some heuristic. So one could conjecture that roughly actually L cubed upon 48 of them, asymptotic with L, for example, right? And that number L cubed upon 48 is premised on the fact that one knows by Serre's conjecture now, and which is proven, that they come from the space of modular forms, and somehow they're forced to come from a limited space of modular forms. They're always in level 1 because these representations are unramified outside L, and somehow you can restrict the weight because. Right, so somehow the heuristic comes from just summing up the dimensions of these spaces using the fact that you know the dimensions. Right, this L cubed upon 48 is exactly this number. Right, and somehow there's a heuristic which tells you that this perhaps could be the answer. And the heuristic is that there should be very few congruences between modular forms in this restricted way. Right, so somehow okay, you know Serre's conjecture, but there's a very basic question you can ask about how many representations are there of a certain sort, or how many model eigensystems are there in level 1, and that is still quite unknown. The upper bound is L cubed upon 48. The best lower bound is L squared upon 8, and there's a big gap, right? But I don't know even how to go from 2 to 2 plus epsilon for any positive epsilon. So yeah, so okay, I'll stop. Yeah, there's some heuristic on this conjecture for this conjecture for this guess.
Thank you very much for the very nice talk. So if we have any question from the audience or from the public on Zoom, you can raise your hand and I can pass you the microphone. So.
Yes. When you say that it's actually of the primes, that's positive density, you mean that the density exists, or just that the lower density is positive?
For which set of primes has positive density? The Starwell congruent zero model? No, which set of primes?
I forget which slide it was where you said that the set of primes, the set of L, the set of had a positive density.
Yeah.
And did that mean that the density actually existed, or just that the lower density was positive?
No, I suppose that meant that the density existed and was non-zero. Yeah, I don't know exactly which one.
Mm-hmm.
Yeah, so you were very fast at the end, so I'm not sure my question will make a lot of sense. But when you want to count those finite representations, they count from modular form. You take the modular form, you reduce them, and you count the number of reduction. But is it hard to do? This is what you mean?
Yeah, because these Hecke action on model space of model forms is not diagonalizable. There's some kind of you cannot diagonalize the space of the modular forms model under the Hecke action. It's not a direct sum of eigenvalues.
Okay.
So there's some nilpotency, but one is conjecturing that it's essentially diagonalizable, at least in this restricted weights.
Okay.
So somehow it's a business about non-semi-simplicity of the Hecke action model. But one
Okay.
expects it to be not that non-semi-simple.
Okay, because it's okay. So if it was not model, it would be okay because you know the number of
Yeah,
elements, the basis, and you reduce
yes.
the model.
Yeah. But on the other hand, it's maybe related to how many weight one modular forms are there, right? In classic 0. It's not related, but that also is a hard question. You have dimension formulas for Sk gamma naught n for k bigger than or equal to 2, but
Yeah.
S1 is tricky.
Yeah,
right?
true.
So it's somehow, it's not really related, but yeah. So that's also a question about counting number of Artin representations into GL to see two-dimensional, which are odd, and there's no easy answer. Yeah.
You count by something like Riemann-Roch theorem, and there's a case where there's a case of Riemann-Roch where you have equality, and is it how you count?
Yeah, exactly. In weight one,
it doesn't work.
Yeah, for weight one, it doesn't work. Yeah.
It's from Shimura's book, I remember.
Yes, and I think Bill Duke, and I think that people have some sort of estimates for this, but it's a delicate case. Yeah. Yeah.
There's your lower bound of L squared. Does that just come from saying in each space there should be at least one and different ways to distinguish them and then you twist?
Yes, that's true. There comes some estimates saying that how many times is L divide BK, and then twisting. Yeah. So this L squared upon it is almost explained just by the reducible case, which is of course you can just count. Maybe you get, I don't know whether you get exactly L squared upon it, but L squared upon something you get. But it's very hard to go beyond L squared. But then L squared is very easy to get. So, and L cubed is also an upper bound. But I think it'll be very interesting to go even a little bit beyond L squared. See, but I see no. Yeah, I've thought about it a little bit.